Welcome. My name is Mr. Sawchuk, and I will be your host for topic 5.5. Just kidding. Welcome. We're doing 5.5 today, and multiplying and dividing a polynomial by a constant is our topic for today. So please pay close attention. Feel free to pause this whenever you need to do so to check on a concept and rewind. That's the nice thing about video. Here we go. All right. So we're going to review a few concepts before we move forward too much here. So simple math, what does it mean if we have 3 times 5? So what it means, if we want to look at that in terms of blocks, so if we had blocks, sorry, we're going to have to shift to the pencil mode here. If we have 3 sets of 5 blocks. So that's one way we can look at it. This would be 3 times 5, with 5 being sets. Or another way to look at it is we could also say that we have 5 sets of 3 blocks. Hopefully this isn't too loud with the pen as I read on the iPad. But, so we have 5 sets here of 3. Either way, we're going to end up with 15 blocks, right? And so alternatively then, if we look in the inverse operation, which happens to be division, the number here is a little bit bigger, and I'm not going to draw it out. But it would mean that we have, if we look at 100, I always like to write division out this manner. Just makes it easier to envision for myself. Is 100 divided by 5 means that we would have 5 sets of 20 blocks. Or if we divide it, we also divide by 5, and that means we would have 20 sets of 5 blocks. So it doesn't matter which way you look at it. You're ending up with smaller chunks of a larger whole. The same is going to apply to polynomials. Right now what we're going to do is, with this slide, we're going to set ourselves up so that we can look at how we would envision things with algebra tiles. Okay, so if we have a rectangle, one side is just simply 3. The other side is, part of the section is 8. The other part of the section of that length is 4. If we wanted to look at that whole length, we would need to add 8 plus 4 to get the whole, right? So in this equation, if we wanted to set up and create a multiplication sentence for this, we would take, if for the area is really what we're talking about. Sorry, I have to be clearer on that. Area is what we're looking at. We'd have to take 3 times 8 plus 4. 3 times 8 plus 4. Again, we can't escape this. You've seen it in your other teachers' lessons from the previous sections. We have to, of course, use BEDMAS. So inside the brackets, we have 3 times 8 plus 4 is 12. Then if we finish that multiplication, we're going to end up with 3 times 12 is 36, and whatever units that's going to be. So our area is equal to 36. And again, this is just revisiting that again. So we have 3 times 8 plus 4, 3 times 12, and 36. Now, let's take a look at this. There's 2 ways where we can represent this whole thing. Remember, when we're looking at algebra tiles, the smaller tiles are a depth, length of x and a width of 1. So each one of these is x by 1, x by 1, x by 1, x by 1, right? But if we look at the whole thing as a whole, then our width is going to be 3, and our length will be 4x. So what if we wanted to find the area in this situation? If we wanted to do that, we would simply take and multiply 3 a little bit. So 3 times 4x. So 3 times 4x, then we can't multiply the x against the 3 necessarily, but we have 4x at 3 times. So basically what we're saying is we have 4x plus 4x plus 4x. The same thing that we considered when we were on the first page. So 4x plus 4x plus 4x. This would be 4x plus 4x is 8x plus another 4x would equal 12x total. So our area for this situation would be 12x. And that's what we're going to find from this on this slide. So if we're looking at this shape here, that's what we're going to create. Is an area of 12x because our length is 4x and 3 is the other. Remembering that our formula, of course, of area equals length times width. I jumped ahead. So that's just simply what we're showing again here is 3 times 4x will give us a total area of 12x. Sorry, that just erase that there. So same thing being shown here is that's what we end up with the area for this shape. All right, what if we took and look at something a little bit different, something a little bit more complicated, such as a polynomial? So if we're taking the algebra tiles and we're representing this shape, we can look at this as 3 sets of a specific number. We can't look at this vertically because there's nothing that gives us 3 equal sets looking up and down. However, if we look at this in a horizontal manner, we have 3 sets that are identical. These 3 sets, remembering that anything that is red is negative and yellow in this circumstance is positive. So if we come up with a sentence or a phrase for this first section, it is simply negative 2m if we consider these m. That just happens to be what we're going to use as variables in this situation. So it'd be 2m plus, and then we have the constants 1, 2, 3, 4, plus 4. So then again, this next one would be negative 2m plus 4, and the following one would also be negative 2m plus 4. So we have 3 sets of these. So we can write this up. We could just simply add this whole thing up. Together. We get 4 plus 4 plus 4 would give us 12, so positive 12. And negative 2m, negative 2m, negative 2m would then give us negative 6m plus 12. We could also look at it in the manner of a multiplication sentence. So if we have 3 sets all the same of negative 2m plus 4, we can then use distributive property to figure this out. So we have to multiply 3 times the negative 2m and then 3 times the negative 4. So 3 times negative 2m, of course, is negative 6m. That's the first part. We have to carry this negative symbol here down, of course. And then we have 3 times positive 4, or plus 4. So the positive will remain since this itself is a positive. So 3 times 4 will equal 12. So either way, whether you look at it in one manner up here, if you look at it here as an addition phrase, adding 3 of the same phrases together, 3 of the same sentences, you have identical sets of tiles. We'll end up with negative 6 plus 12. Or if you multiply by 3, you end up with the same sort of set through multiplication. And you end up with negative 6m plus 12. So that's really what we're representing when we come up with these multiplication sentences, is we're representing the same thing we would do with addition. And when we're dealing with polynomials, it's really no different than we've done before using distributive properties or dealing with just simple multiplication, 3 times 4, 3 times 12, 3 times 6. It all is really doing the same thing. It just looks a little more complicated But the thing is that you need to remember is you need to take it step by step. So if we revisit the same problem here, same polynomial, 3 times 2m. So what is 3 times negative 2? Negative 2 times 3 is negative 6. The m goes with it. And then 3 times positive 4. I always like to look as plus as a positive, which you can either say plus 4 or positive 4. You're going to end up with plus 12. So if you do it step by step, it makes it a lot more simple. If you look at the whole thing all at once, it's going to look a little more scary, if you want to use that phrase. But break it into the simple steps, do one step at a time, and that's going to make it easier. So you have to be patient and you have to be willing to trust through the process. Okay, so let's give a few of these a try. So here we have negative 2x minus 5. So negative 2 times x. It's supposed to be a negative, it's not showing up very well. So negative 2 times x will be negative 2x. And negative 2 times negative 5. So remembering that a negative times a negative will be a positive. So we'll end up with negative 2x plus 10. Let's work through this one here. So I'm going to start moving these separate so it makes it a little bit easier to see. So number 2, we have 3 times negative 2w minus 7. 3 times negative 2 is negative 6. The w goes with it. And 3 times negative 7, there's as this positive times a negative will give us a negative, so negative 3 will be negative 21. So that will be our final answer there. For the next one, we simply have a negative out front of 3x minus 9. Now, this is what I tell my students, I'm sure you guys have heard this, is that you can also look at negative as just simply saying a negative 1. So it's the same as saying negative 1 times 3x, negative 1 times 9. And so if we take negative 1 times negative 3x, we get negative 3x, and we distribute negative 1 times negative 9, so it's a negative times a negative equals a positive, so we get a plus 9. So our final answer in this one would be negative 3x plus 9. The following one, it gets a little bit bigger than that. And you can feel free to use your calculators if you need to. So now we have negative 4 outside times 3v plus 23. So negative 4 times positive 3 will be negative 12, carry the v, plus, and if you don't have a calculator, you're going to have to do a little bit of long multiplication here, but negative 4 times positive 23 will be, so I have to do it in my head now, 8, 9, will be 92. But being that it is a positive times a negative, we will end up with a negative number. So we end up with another negative in this situation, so negative 12 minus 92. So in the next page, you're going to see everything. Oh, there is a mistake on this page. I did not count before. So anyway, this part here should be 92. This part here should be 92. My apologies for that, you guys. So if you look through, and what this is simply doing is it's breaking into each of the steps. So this first part here is negative 2 times the x. This second part here is negative 2 times the negative 5 to show that it's 10, and then it's putting together in the fourth step. So it breaks it down into something a little bit simpler than what I was doing. I talked through it on the previous page, but I didn't make it visual. So on this page, it's a little more visual than it was before. All right.